Hi, welcome to another video here in my channel and my first tutorial involving number system conversion. I'm only going to be covering two conversions. The first one is from decimal to binary and the second one is from octal to hexadecimal. Before we start, I'll be giving a short review to what these number systems are so that it will be less confusing during the conversion. First is the decimal number system, which is the most simplest and commonly used number system. It came from the Latin word decimus, which means 10, consisting numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Second is the binary number system, which is the most useful in computer technology, programming languages, and is helpful in digital encoding. From the word bi that means 2, it consists of numbers 0 and 1. Third is the octal number system, which is widely used in computing on some systems employing 6-bit, 12-bit, 24-bit, or 36-bit words. From the word octa, meaning 8, it consists of numbers from 0, 1, 2, 3, 4, 5, 6, and 7. Lastly, the hexadecimal number system, which is commonly used in computer programming and microprocessors, consists of values from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Our first conversion is from decimal to binary. So we have two methods and I'll be using the first one, which I think is much more complex. Before we proceed, it is important to first create a table consisting the powers of 2. We are also going to include the number 1 as the first digit, so 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 6 is 64, and 2 to the power of 7 is 128. So say for example, 199 base 10. We need to find a number from this table that is closest to 199 but does not exceed its value, because we can't have a negative number as a result. So the closest number to 199 is 128. So from here we subtract 128 from 199, and the answer is 71. Now you need to mark the number from the table that you've just used, and we'll get to that later. Now from 71, we again need to find a value on the table that is close to it, which is 64, and subtracting 64 from 71 would give us 7. Now you need to mark 64 on the table. Now from 7, the closest number is 4. So we subtract 4 from 7, that is equals to 3. Now let's mark 4 from the table. Now from 3, the closest number is 2. So we subtract 2 by 3. That would give us 1. Now the obvious subtrahend to 1 is 1. And subtracting 1 to 1 would give us 0. The clear goal here is to subtract the given value to the table until the difference becomes 0. Now as we see here in the table, we have marked values 128, 64, 4, 2, and 1. All of the number that we have put a mark, we'll put 1 at the bottom. Let me erase this. And to those values that doesn't have a mark, we will put 0 at the bottom. So we'll read the numbers from left to right and add a base 2 at the bottom. So 1100111 base 2. So the decimal number 199 is equals to binary number 11000011. 1. The next method involves division, and it also gives us the same answer from the first method. We're going to use the number 199 base 10 again and convert it to binary. Since we are going to convert it to binary, we will use a divisor of 2, or in other words, we will divide it by 2. So 199 divided by 2 is equals to 99.5. Now instead of putting 99.5, we will put it as 99 R1. Now the R1 signifies that there is a leftover which you cannot use as our next dividend. And again, we'll use 99 and divide it by 2. So that is equals to 49.5, or 49 remainder 1. Now from 49, let's divide it by 2. That is equals to 24.5, or 24 remainder 1. Now 24 divided by 2 is equals to 12, or 12 remainder 0, because there's no leftover from the quotient. And then 12 divided by 2 is equals to 6, or 6 remainder 0. 6 divided by 2 is equals to 3, or 3 remainder 0. Now 3 divided by 2 is equals to 1.5 rather, or 1 remainder 1. Now 1 divided by 2 is equals to 0.5, or 0 remainder 1. Now from here you need to arrange the numbers from the most significant bit to the least significant bit, or read it from bottom to top, which gives us 1 1 0 0 0 1 1 1 base 2. And that is how we convert decimal to binary in this method. Our second conversion is from octal to hexadecimal. It may sound as one conversion, but we actually use two. A conversion inside a conversion. We convert the octal first to binary, base 8 into base 2, and then convert it to hexadecimal, which is base 16. Let's say, for example, 521 base 8. So to convert it to binary, we need to separate the numbers first. 5, 2, and 1. Now we'll put the powers of 2 at the bottom, mainly 4, 2, 1, 4, 2, 1, 4, 2, 1. Now, these numbers add up to 7, which is the largest or maximum number in the octal numerical system. We then mark those bottom numbers that add to the octal above. So 4 and 1 is equals to 5. Now the 2 is equals to 2. The 1 is equals to 1. So the marked numbers, we will put 1s at the bottom and 0s to the unmarked. From here, we arrange the binary numbers to 4. So 1, 2, 3, 4. So 1, 2, 3, 4. 1, 2, 3, 4. So 0, 0, 0, 1. 0, 1, 0, 1. And 0, 0, 0, 1. Base 2. So we just added 3 zeros from here, from the first place, so it could become a group of 4. If we convert it to hexadecimal, we again put the powers of 2 at the bottom. So let's write the binary first. And add the powers of 2 from the bottom, that is 1, 2, 4, 8, 2, 4, 8, 2, 4, 8. Now 8, 4, 2, and 1, adding it will give us to 15. Now 15 is the maximum or the largest number from the hexadecimal number system. Now here, we mark the numbers at the bottom that has the 1s above it. So in this case, we have here 1. We have here 4, 1. Here 1. Now, what we'll do here is multiply the powers of 2 to the binary numbers at the top. So 4 times 1 is equals to 4. 1 times 1 is equals to 1. 1 times 1 is equals to 1. And then from here, we add the numbers. Now this one doesn't have any numbers beside him. This one has, this one doesn't. So we'll add 4 and 1, that is equals to 5. This is 1, this is 1. So combine it together, that is 151. Let me erase this first. So 521 base 8 is equals to 151 base 16. That is how to convert octal to hexadecimal. So to check if your answer is correct, you need to convert both the octal number and hexadecimal number to base 10 or decimal number. So let's put 521 first. Base 8. So we'll put the powers of 8 to the bottom. 8 to the power of 0. Sorry. 8 to the power of 1. And 8 to the power of 2. Now, we will multiply 5 by the 8 to the power of 2. Then add 2 times 8 to the power of 1. plus 1 times a to the power of 0. That would be, so a to the power of 2 is 64. 64 times 5 is equals to 320. Plus a to the power of 1 is 8 times 2. That is 16. Plus a to the power of 0 times 1. That 8 to the power of 0 is 0 times 1 is equals to 0. So 320 plus 16 is equals to 336. Let's erase that. Now second is 151. Since this is a hexadecimal number, we'll put the power of 60 to the bottom. 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. 1 times 16 to the power of 2 plus 5 times 16 to the power of 1 plus 1 times 16 to the power of 0. So 16 to the power of 2 is 256 times 1 is equals to 256. 16 to the power of 1 is 16 times 5 is equals to 80 plus 16 to the power of 0 is 0 times 1 is equals to 0. So 256 plus 80 is equals to 336. Therefore, our answer is correct. That's all for this video, and I hope I explained it clearly to you. Stay safe and thank you for watching.